Hello, I'm Ferdinando Fioretto. I'm an assistant professor at Syracuse University. I'm ecstatic and deeply honored to be selected as this year's Early Career Research Awardee, and I like to thank my nominee and supporters, as well as the selection committee. So my research focuses on two main areas. It studies how to use machine learning for solving complex optimization problems, and also how to make AI algorithms better aligned with societal values, especially privacy and fairness. So both areas use tools from constraint optimization, and this talk will focus only on the first topic, which develops machine learning models to speed up decision-making processes. So let's start with some motivations. Critical engineering systems, including power grids, supply chain, flood mitigation systems, transportation systems, they are systems that playing a crucial role in ensuring social and economic stability. Their operations relying on solving sophisticated optimization problems and have been highly stable and reliable in the last decades. However, with the rapid modernization is introducing significant challenges. Think about the integration of renewable energy sources in power network or the return policies in supply chains. So all this is creating notable uncertainty around supply and demand, complicating the operations of those systems. So in response to those challenges, system operators, they must now develop solutions that are robust to different operating conditions. So integrating uncertain predictions within the decision-making process. So these new problems create substantial computational challenges, currently forcing system operators to produce suboptimal solutions that then translate in significant economical and societal costs. So take the electrical power system. It is the largest machine built by humankind. Every year in the United States alone, about $400 billion worth of electricity is produced and shipped through the transmission system. It has also a massive climate impact, with about 40% of total carbon footprint produced from electricity generation through the combustion of fossil fuels. And so improving the efficiency of these systems, even slightly, would produce massive benefits for the population at large. And to give you a sense of the problems that we're dealing with, take a look at the optimal power flow illustrated here on the right. So this is a problem which is solved repeatedly at different time horizons. And in a nutshell, what it does is determining the generator, the most cost-efficient generator dispatch that meets the power demands while satisfying the physical and engineering constraints in the power system. It's a really difficult problem. It's not convex, not linear, and needs to be solved with very high frequencies. But the resolution frequency to solve this optimization problem, it's limited by the computational complexity of it. And so to address this issue, what system operators do is not solving this full nonlinear problem, but they solve a relaxation or an approximation of it. And so while this is more efficient computationally, these simplifications also bring suboptimality, which induce costs, both in an economic perspective as well as in a societal perspective at large. So the question here is, can we build better approximations, and how? So by building those approximations is really a non-trivial task. It's in general problem specific, it involves a lot of optimization theory. And thus, our idea here is that of taking the problem, dealing with this problem and looking at it from a slightly different angle. So we have this original constraint problem, O, our optimal power flow, which is abstracted as follow. And what we want to do is to derive a reliable approximations, O tilde, of the problem O. And thus we ask, is it possible to take a data-driven approach to learn to approximate the original problem? And to answer to this question, we have developed a framework that tightly integrates discrete and continuous optimization with machine learning to provide near-optimal approximation to our problem of interest. And this is motivated by engineering systems like the power network, which produce massive amount of data solving optimization problems repeatedly. So the learning task takes as input some data, which describe the problem inputs and its characteristics and its associated solutions. And what it does is it learns to estimate a parametric version of the original minimizer, the original problem O, to obtain a strong approximation of it. Now, in our context, this is represented by a neural network, and this neural network should ideally solve the following problem, the following empirical risk minimization problem, which minimizes the prediction error, but it's also subject to the constraint of the problem. And the main difficulty here lies in the constraints, which can represent hard physical and operational limits, and they cannot be explicitly taken into account in a machine learning model. So a naive approach that ignores those constraints is most likely to result in predictions that significantly violate them, as I will show you later. And so the question here is, how do we enable deep learning models to take into account of these constraints during their predictions? And so my group has proposed several integration of discrete and continuous optimization and learning to do so. In particular, one solution exploits Lagrangian duality, where the learning task is continuously augmented with constraint violations. And so the constraints violation that we are experiencing during training. And we do so in order to learn to produce strong approximation of the original problem while also learning to satisfy the underlying constraints. So when we're applying this approach to the optimal power flow problem that I've introduced earlier, this deep constraint learning framework, which is highlighted red here, shows very promising results. So the table shows results for 3 representative test cases of increasing difficulty. And the main comparison I want to focus on is against this blue model, which is the current industry standard, while this model here shows instead the same neural network that we are using in this deep constraint learning framework, except we don't deal with the constraints, just the pure minimization of the errors. So the first table shows how far are the predictions outputs with respect to the closest feasible solution, which is to say, how close are we to satisfy the constraints of the full nonlinear model? And here you can see that our model brings over 1 order magnitude improvement. The second table shows the improvements in terms of cost, which is showing that our model here brings, it's about 0.2%, well, yeah, is within about 2% of optimality and over 1 order magnitude more precise than the industry standard. And finally, if we look at runtime, then we can see that those models, so the inference time, it's obviously way faster than solving an optimization problem, and so it brings over 3 order of magnitude of speed ups. So this means that we're really on the right track here, because system operators may now respond to events extremely quickly, events that are uncertain, and use those type of approximations that really deliver unprecedented accuracy. But so this seems to work really well, and next we asked, why can we construct such good approximations in practice? Firstly, if you take a look at the figure on the top, which is showing generators' outputs with solid lines at the varying of the inputs demand, we notice that the solution trajectories that is associated with the problem instances on various input parameters can be naturally approximated by piecewise linear functions. And so there is a recent result by Huang et al., which shows that ReLU neural networks have the ability to capture piecewise linear function. In the example here, we illustrate that a model equipped with the ReLU activation, the dotted line, and compare it with a model equipped with the TANH activation, the dashed lines. And we can see that the ReLU network does in fact do a much better job in approximating the solution's trajectories. However, while these models are compatible with the task of predicting the solutions of an optimization problem, the model capacity that is required, so the number of parameters of the model that is required to represent a target piecewise linear function exactly, depends directly on the complexity of this piecewise linear function, so on the number of constituent pieces and its total variation. In a recent paper, we have characterized the error that is associated with the classes of functions that can be learned by a ReLU network with the fixed capacity with respect to a target trajectory. And so in the bottom figure, we plot the prediction errors as a functions of the complexity of the output trajectory associated with each decision variables for a number of problem instances. And highlighted red, we have highlighted red here in the bottom of the figures, we have solutions that corresponds to linear trajectories, so very easy to capture. And they, in fact, have typically low predictions error, while the error increases as the complexity of the piecewise linear functions associated to those trajectories here increases. Now, when many variables have a simple solution trajectories, then highly accurate approximation can just be obtained by a ReLU neural network, even if we ignore the problem constraints. So this is the case for some of the benchmark that we're using, but the vast majority of those benchmarks that presents indeed difficulties for these ReLU networks. And so in theory, as we have recently shown, it is to be expected that large deep neural network models will be better suited to learn more complex solution trajectories. However, this aspect is not consistently observed in our experiments. Excuse me. In fact, so this is not consistently observed in our experiments. So the figure here on the bottom illustrates this surprising behaviors for three generators, so three outputs with complex trajectories, and showing that the predictions errors do not necessarily decrease at the increasing of the model size. And so this is surprising behavior. To understand why it occurs, we examined the dynamics of those highly volatile solutions trajectories at as those ones that are highlighted in these figures. So the figure here shows the trajectory of three generators, the solid lines at varying of the inputs, and their associated upper bounds limits, the dashed lines. So the shaded area highlights the regions in which large volatilities are observed, and this region also corresponds to the portions associated with the higher dispatch errors, so the higher predictions errors. So the bottom plot shows instead results, shows the trajectories of voltage magnitude values for a selection of buses. So those are quantities that are really not directly associated with the outputs predictions, but they are linked to them via constraints. In fact, here we can appreciate in this volatile region how those variables are touching their upper bounds limit, which is denoted with this red dashed line. So this is telling us that these predictions error are arising as the hidden representation of the neural network does not accurately learn the operational and physical constraints which are regulating the behavior of the optimal power flow solutions. In other words, the model is unaware of those constraints. When constraints are explicitly encoded into the model, either via the Lagrangian duality method that I mentioned earlier or through other approaches that we've studied, those behaviors largely disappear, obtaining highly accurate predictions. And so this is a really interesting result. But these results here apply naturally to several nonlinear constraint problems. And so the next natural question is, how about combinatorial problems? Can we learn the underlying combinatorial structure of a problem? And I want to anticipate that we're far, far away from answering this question, but we and several groups in this nascent community at the intersection of constraints and machine learning have started tackling this challenge. And so we look at scheduling problems. They are combinatorial optimization problems. We're given a set of jobs of varying processing times, which needs to be scheduled on a set of machines with varying processing power. And the goal here is to minimize the total length of the schedule. So those are extremely hard problems to solve within real time or short time constraints. So beside the difficulty of handling constraints in this setting, we have observed recently two interesting challenges. So the first is the presence of multiple symmetric solutions, and the second is the use of approximate solvers, so approximate or randomized solvers used to generate the training data. So a standard approach to the generation of the training data in this context here would take each individual instance independently and use some state-of-the-art optimization solver to produce the labels, and then use those labels to train our model. However, this may create some significant issues. So this clip here on the right shows that solutions problem which differ only by slowing down the tasks on one machine by 1 second at a time can produce vastly different solutions from one another. And so you notice how those tasks are switching. So this implies that the underlying scheduling trajectory for a given task is highly volatile, which poses serious challenges for the learning task. So as a result, when we are creating a training dataset, we could generate a combinatorial number of possible trajectories. And thus we asked whether we could modify the data generation process to obtain datasets which are more amenable to training. So while equally valid as optimal solutions, some sets follow patterns which are more meaningful and recognizable. So for example, in this diagram, a pictorial illustration, we show that some combinations of solutions that we found to our problems for varying inputs may have better, more recognizable patterns than others. And so without going too much into the details, at a high level, the data generation process, which we recently proposed, encourages solutions of closed input to also be closed with respect to some given distance notion, while searching among the space of symmetric solutions or given a lower bound on their costs. And so the resulting data generation process, which is heuristic in nature, but if we compare the standard approach, which is here on the left, to generate training data sets, and the one that we're proposing here on the right, then we can clearly observe that the solutions on the right are much less volatile, while retaining exact or similar cost with respect to the one on the left. And so when we apply when we train a Lagrangian dual-based model with this data set and compare the solution reported by this learning approach against those reported by CP Optimizer, which is a state-of-the-art solver, which uses large neighboring search in order to tackle this problem, we observe the following. Well, firstly, now given enough time, the CP solver will outperform the learning-based approaches, in part because the training data is generated imposing a timeout, which is 30 minutes in our case, and thus the learning can only be as good as the provided labels. But the goal here is to provide very quick approximations to the problem solutions. So we first observe that it takes the CP solver about 12 seconds to outperform a model which is trained with the standard labels, which is not shown in this slide. But in contrast, the CP solver takes about 1 order of magnitude longer to outperform the same network when this network is trained with the optimized labels that I just mentioned earlier. And so it is even not able to do so within 30 minutes on 3 out of 20 GSP lib test cases that we studied. And so here the diagrams, the plots are showing the optimality gaps retrieved by the CP solvers versus the solutions that is found by the learning-based approach as the runtime goes by. So those results are really encouraging as they show us that there's a significant opportunity to leverage learning-based methods combined with constraint optimization knowledge to approximating challenging constraint problems in near real time. Although there are many challenges that face the development of these exciting areas, and we're just scratching the surface. So while I focused on power system and scheduling, these methodologies are general purpose, and we have also been applying them for approximating other optimization problems in gas network, trans-precision computing, task allocation problems, and to learn non-discriminatory classifiers. So to conclude, this talk covered an area at the intersection of constraints and machine learning, which I'm really excited about. We were motivated by the desire of improving the efficiency of critical engineering system operations. We developed an integration of machine learning and optimization that enable us to solve large-scale decision-making problems featuring complex physical and engineering constraints. We also try to shed light on why certain behaviors occur, as well as study method to generate training data to aid the learning of combinatorial problems. And while this research is still in an early stage of their development, I strongly believe that the integration between combinatorial optimization and machine learning is a promising direction for the development of new and transformative tools in combinatorial optimization learning. So I want to thank you, and I want to also thank my amazing students and collaborators and the sponsors that are supporting my research.